the Kepler satellite's targets with follow-on spectral observations by Charles Paxson. The Giant Magellan Telescope has a mission to find large terrestrial planets by the method of precision radial velocity shifts in the spectra. The Harvard-Smithsonian Astrophysical Observatory in Cambridge, Mass. Has the responsibility and honor of supplying the first light spectrometer to the Giant Magellan Telescope. Here's an artistic rendition of the future. It's Chile and the Atacama Desert. The anticipated year for completion is 2022. The spectrometer will record high-resolution spectra. Shifts in those spectra, as shown here just as a representative example, will show shifting in the spectral lines, and those shifts in wavelengths are proportional to the velocity of the star. The star moves in response to planets orbiting around it, and if data is recorded several nights over the course of the period of some of those planets, it will be able to make a mapping and a sinusoidal oscillation of the motion of that star to indicate a planet. So these observations are expensive in and of themselves just for a night, but to find planets you have to observe the same star for many nights, maybe over the course of days, months, years. It would be very advantageous if there was some way to know in advance that the star has the potential for planets or is more likely to have planets than other stars, if our mission is to find Earth-sized planets around stars. So the idea here is maybe we can use data from past missions to create an artificial intelligent system that may help us in that endeavor. Kepler mission has been flying for the last 9 years. It's identified 2,300 planets, around about 1,000 stars. And people are now currently following up, looking at those identified stars with their ground-based telescopes recording spectra. So the Kepler telescope finds planets by the method of the transit method. So if a planet passes in front of the star and that planet happens to be oriented between us and the star, then the light that we record of that star will dip ever so slightly, and that periodic dipping then will define the period of the planet as it orbits the star. Knowing these orbital periods gives us other parameters of the orbital system, such as the mass of the planets and the star, etc. So now that we have, by an independent method, identified stars that have planets, and we are going ahead with the next step of recording spectra on those stars to confirm or claim that there's a false positive finding by Kepler. Those spectra then can be used to be analyzed. So we have a set of spectra that are on stars with planets and a set of spectra on stars without. And with this set of data, I intend to use these deep learning with these relatively low resolution spectra and see if we can figure out a way to have a deep learning system indicate the signatures of planets. The hypothesis is that, and that has been discussed in the astronomy literature, is that the metal abundances on stars with the host planets are lower than the stars that stand alone. So the idea is that the planets are taking up some of the irons and the calciums and the sodiums as the planetary system and stars being formed. So the stars left with less iron, less calcium, sodium, and those elements are caught up in the planets. So by measuring those spectral lines, we may be able to see a difference between stars with planets and without. So to that end, I took a typical star that was recorded, and this is by Kepler, indicates no planets around this star, and I want that type of spectra to first, because if I took a star with planets, well then it may have its spectra altered, and and I don't know in what way that was altered. So I'm going to take a star that was standalone. I'm overlaying then National Institute of Standard iron transition lines over the plots, and where I see that the transition lines are encased in the absorption lines of the star, and I did several of them. I don't think I caught every one of them, but I found 13 in all, and I can see several more that I could do. But I identified those 13 spectral features, and with those 13 spectral features, I cut them out of the data set and will stitch them together to use as training data. So here's an example of what I did with that star that we were just looking at, the KOI6, which is the identifier in the Kepler database. And here are the lines that I cut and how I cut them. And we will see in my training data set how they look when they're stitched together. So once these centers and these bandwidths have been identified, now I have a turn the crank software system to cut the same spectra out of every star that I'm going to analyze and get that little sector of spectrum out of it and use it as the training, test, and validation set that is going to help learn the difference between stars with and without planets. Now, in the course of pulling this data, I was completely had no idea where to get the data. I was led to the Kepler database, and Kepler, that mission now they have set up a site so that astronomers can contribute their independent work and their ground-based work and upload it to the NASA Kepler site. So the database it needs to be registered for. There's a password system, and it is not easily accessed. So each star has to be treated separately. When you download a set of data and you want spectra, you also get images, light curves, other properties of the star, and it totals something on the order of 3/4 of a gigabyte of data for each star. So I managed to get 50 stars down, and there was preponderance. There was one way of creating the FITS files that was pretty standard, and it was a lot of the observations from the Keck Observatory in Pasadena, California. But there was several sets of data that have data of different types, so that needs to be further investigated. So I took what was available to me and set up a script to load up the spectrum and cut out the spectral pieces as I described, and set up a training system to just kind of mock the idea up. I understand as I got more and more into this that there are a lot of details in astrophysics nature that have to be considered because they would confuse the network. If we're just trying to isolate differences between a star with planets and a star without, then we've got to control a lot of factors. So first of all, iron lines, they may or may not be present in any particular star that we're looking at. We have the star's temperature, and for instance, transitions that happen in the outer shells of the iron atom are not going to be present in stars that are very hot. So cooler stars, we might see those type of lines. Hotter stars, we won't. So in this analysis, I didn't consider that. It was too much work for the couple of days that I investigated this problem. Host stars are stars that have planets, host stars, are in a reactive orbital motion to the planets. So they, in general, if I'm looking at a star that has planets, it's moving. And its relative motion at phase 0 will be 0, but everywhere else it's going to be moving blue shift or red shift from me. And so I will want to um, figure out a way to record stars that have planets at the near the phase zero time, so that the motion, the relative motion, is zero. And so that way I'm comparing stars without planets that are still in relationship to us. I'll be comparing apples to apples in that way, not one moving and not the other not moving. Stellar types may need to be considered. So we have most of the stars that I selected are between the 5,000 and 6,000 Kelvin temperatures, which is kind of a type G star. But there's several other types of stars. So it'll be A Fine Girl Kiss Me is the poem that allows you the different types of stars, O, K, B, F, M. And each of those stars are different sizes and masses and temperatures. So, and that affects what the spectrum looks like. And so there might need to be some more control for the type of stars that we're comparing in the stars with planets and stars without. It might have to be broken up according to stellar type. And if that's the case, then I have very low numbers, and that would be a concern. Iron lines were selected, but there's other important lines like calcium and sodium that I would like to investigate. And then also there's the idea of, rather than selecting the lines that I selected, I could do further processing and calculate an equivalent width of each line, which is kind of a standard way in astronomy of considering stellar spectrum. So what I've done then is stellar spectral features of iron in fluence absorption lines have been utilized in creating a mock-up of a training test and validation data that will be used in the softmax regression. The Kepler data archive has been utilized. It is anticipated that several months of data processing would be required before secure training could begin. So let me show you then a little bit of the data processing that was required in the script that is included in this package to get the data. So here it is. It's annotated and describes here at the top of the 6 main steps that were used to cut this data. Here's a list of the spectrum that were used, the different file names, the Kepler types, the temperatures. I started to enter the temperatures, but since I'm not using the temperatures in the analysis, I didn't complete that part of the project. And then indicate which planets, with the planets key, which are true and false. So I just have a few non-planets spectra, because that data, when I started exploring it, it's got a different file read template, so I need to do more work to get myself an even number of stars with planets as stars without. When I'm going to take all this data, cut it up, and drop it into a pickle file, and I'm going to one-hot code it with the 2 choices that I'm creating. Simple linear regression, I just swiped this from the web, but these equations are directly out of my statistics books, and I just used it because I wanted to take a look at the continuum of the spectra and do a little quick statistics with it. And everything in this notebook is what I've written and developed. Here's to load the spectrum. From the NIST website, I downloaded, I don't know, I think it's several thousand lines, or a couple thousand lines of iron transition lines, and formatted those so that I could use them and overplot them on my spectra. There was some normalization that I wanted to do to kind of each of these spectra vary in intensity according to their distance from the Earth, and and on how much signal to noise the settings were for observations of that object. So to take that variation out, I normalized them. Although the normalization didn't quite work, as I saw it, I'll show an example of some of this stitched up spectra, and they're not all sitting at around 1, so something's not quite right with that calculation. Here is the calculation. I used just kind of standard statistics and data processing. Here's some of the plotting analysis to make the plots, and here are some of the main analysis plots. So here's a whole region of, it's called the R spectrum in the Kepler nomenclature. And here's a fitting line that I made at the continuum that I'm going to subtract out so that I could just analyze all these lines. And here are the then pieces of this spectra in 100 angstrom, 100 angstrom segments. So the lines were overlaid, and then I identified with an X where the centers are. Although here, I'm calling this a center, but it's the center of this whole width here, so that I'm getting the entire spectral feature from continuum to continuum, and the center is here rather than right on this line. But that's just the style that I use to get this whole line. So I need to go back and analyze these lines, whether these lines are actually present in this star, and that will be determined by considering the temperature. And there's a whole set of lines, and I can investigate other wave bands. Excuse me. So then this set here is my results, basically, and now I've identified the band centers and the band wavelengths, the high and low wavelength, so it identifies the band pass. And it's that I'm going to use in this neural net spectrum data, where I'm churning through the data and just cutting up according to these centers and bandwidths. And here's a little processing routine to do just that. And then I'm left with, for one spectra, here's all the data cut up and plotted along the couple hundred angstrom that I was showing earlier. Okay, and so now I'm going through and processing all the data. Some of the data format is not readable for some reason, so I just reported what's problematic, and this was just for illustration purposes for one of my slides. So then the data that was generated, I store in a pickle file, and then pull in with the my softmax regression suite of software. So all of this software, this was taken from the Geeks for Geeks. It was a very nicely documented softmax regression notebook. I had to change it for the particular data size that I had, that I was using 2 elements for my 1-hot encoding instead of 10 that the data said. So there wasn't much alteration that I had to make, but this is going to be a good start for testing whether this idea is feasible. I imagine that with the low numbers that we have, I'll want to do some k-fold transition to help me stretch my data. Here's an example of that data that's being then stitched together. So here with the 1-hot coding, this 1,0 indicates this is the set of spectral features from a star with planets. Here's one without planets, and then these other 2 are with planets. And I don't know, they look a little bit different here. I don't know if that's significant, and we'll see after we get the numbers up. So I just pushed through the what it would take to just get a system working for myself if I had enough data. and it's just to be formal about it and restart and run all. It runs. It takes in a limited amount of data and does tests. And it'll give you typically high accuracy, and sometimes because I randomize the order of my data set to get a set for testing, validation, and training, they jumble up, and sometimes I get a validation accuracy of 0 and sometimes 100, but those are pretty much meaningless because I have so few data. But we will get some data over time and see if this idea has any legs. So that's it. That is my project, and it's been informative. And we will, if the idea takes hold, it'll be very serviceable for the Giant Magellan Telescope, as well as other European large telescopes that are going up. There's a telescope called HARPS, is another high-resolution spectrometer system that was part of the discovery of a very nearby planet reported in Nature last year, Proxima. And so this could be a publishable result with given enough effort and work, and we'll see if we have the funding and the time for it over the next year. So thank you, and this course has been informative. Take care.